In this video, I'll be talking about vector quantization. Basically, vector quantization is a lossy data compression technique. So, I will take an example to show what is lossy in this compression technique and how does vector quantization compress data. So, first I will take a example where I have one-dimensional data. So, for example, I have 8 numbers. Let's say I have 8 numbers. I will represent them in a one-dimensional line. I'll change the color. Okay. And yeah, let's say I have number from 0 to maybe 7. That makes 8, and this point be 7.9 or something like that. So 0, 1, 2, 3, 4, 5. So I have 8 numbers on this one-dimensional line. So this is basically only one dimension. If I want to represent these 8 numbers in binary, how many bits do I need to represent these? So it's basically 8 numbers. So 8 is nothing but 2 power 3. So I need 3 bits to represent these 8 numbers. Now let's use the same numbers. I'll just copy this line and I will paste it. So I have one more copy of that. So if I use same one-dimensional numbers and if I compress them using vector quantization, how many bits will I need to represent these 8 numbers? Let's talk about the first thing that I will do using vector quantization. So basically what I will do is all the numbers from 0 to 1, that's 1.9, I will represent them by 1, and 2 to 3.9 maybe I'll represent them by 3, and from 4 to 5.9 I'll represent them by 5, and 6 to and this region I'll represent it by 7. So instead of having 8 numbers, I will just have 4 numbers. For example, 0 and 1 are represented by 1. That means if ever I get a 0, I will tell it as 1. If ever I get a 4, I will tell it as 5. If ever I get a 5, it's a 5. So it's basically we have 4 numbers to be shown in binary, to be represented. So we have 4 is nothing but 2 power 2. So we have 2 bits to represent the same 8 numbers after using vector quantization. That's 0, 0, 0, 1, 1, 0, 1, 1. Here we had something like 0, 0, 0, 0, 0, 1, 0, 1, 0 till dot etc. till 1, 1, 1. You may be wondering, what did we achieve by using vector quantization here, and by what did we achieve by representing these two numbers by 1, or 2 and 3 by 3. Let's take example of a data set. For example, I will take a few numbers as a data set. So my data set will be, I will take a data set. So it's we'll take it as 5, 0, 3, 6 and 2. So this is my data set. If I would have directly represented it using the first method, that is using these 8 bits, so each of them, if I would have turned them into binary, because everything is stored in memory by as bits, so it's basically binary, I would have represented this by 3 bits, this by 3 bits, 3, 3, 3. So 3 and I have 5 numbers, it becomes 15 bits. So I wanted 15 bits without using vector quantization. So if I would have used vector quantization, I would have changed these numbers to their representation. It's like 0 and initially I have 5. So I have 5, I'll take 5. So after using vector quantization, it will be like 5 is represented by 5, it will remain as 5, and 0 is represented by 1, so 1, and 3 is represented by 3, so it will remain as 3. 6 is represented by 7, so this will become 7 after vector quantization, and 2 is represented by 3. So you may be thinking, what did we achieve then other than changing the numbers from 50362 to 51373? This may not be this may not be like 50,362, it's just 50362. So what did we achieve by changing these numbers from 51373? It's basically how we represent these in memory, is binary. So each number here requires 2 bits. So basically, how many bits do we use? It's 10 bits, because 5 is represented by 2 bits, that's 1 0. It's 5 is represented by 1 0, and 3 is represented by 0 1, and 1 is represented by 0 0. So we use 2 bits for each of them, and in binary it will take 10 bits. So if I have a data set which has around 1000 numbers, then without using vector quantization, I will be using 3000 bits. With vector quantization, I'll be using just 2000 bits. So due to compression, that is through vector quantization, I save 1000 bits. Of course, there is some modification in data. For example, this number and this number doesn't look the same because it's 0 and it's 1, 6 and 2. So it's called lossy. That is, after compression and decompression, we don't get the same original data. There is some changes in the data after compressing and decompressing, because after decompression we get this data. So it's called lossy, and because it saves memory, it compresses the data. So it's lossy data compression technique. I will take one more example to explain vector quantization, but this time in a 2-dimensional space. It's basically 2D data set. I've already pasted one of the examples here in the screen. So let's consider this as a 2D data set. It's 2D because I have a x-axis